Welcome back to DeepVisus, where vision meets depth. I'm your host, and in today's episode, we're going even deeper into the architecture of the brain, exploring how its intricate wiring shapes its dynamic activity, and how scientists are building sophisticated models to understand this profound relationship. Our journey today is guided by chapters 16 and 17 from the insightful book Neural Fields Theory and Applications, published in 2014. Specifically, we'll be drawing from Chapter 16, Large-Scale Brain Networks of Neural Fields by Viktor Jirsa, and Chapter 17, Neural Fields, Masses and Bayesian Modeling by Dimitris A, Pinotsis and Karl J, Friston. So, for today's central question, how does the brain's physical structure, its vast network of connections, fundamentally determine its dynamic activity, and how can we use advanced computational models and real brain data to uncover these secrets? To answer this, let's start with how the brain is wired. Chapter 16, by Viktor Jirsa, highlights that brain connectivity isn't uniform. It's a fascinating mix of two main types. Local connectivity. Think of this as the short-range connections between neurons that are very close to each other, typically within a centimeter. These are generally unmyelinated, meaning signals travel relatively slowly and their connection density tends to decrease smoothly with distance. Global connectivity. This refers to the long-range connections that link distant brain areas. These are myelinated, allowing for much faster signal transmission, but they are also sparse and highly specific. This intricate map of long-range connections is often referred to as the connectome, essentially the brain's unique wiring diagram. Jirsa emphasizes that understanding the brain's dynamics requires incorporating both types of connectivity, along with the crucial element of time delays in signal transmission. Earlier models often used homogeneous approximations, simplifying the brain's wiring for computational ease. While these were useful for some phenomena, they couldn't capture the full richness of whole brain dynamics. This led to the rise of connectome-based modeling, which integrates realistic anatomical data often obtained from advanced brain imaging techniques like diffusion tensor imaging, or DTI, and diffusion spectrum imaging, or DSI, directly into large-scale brain models. This approach reveals how the underlying anatomical structure profoundly shapes the brain's dynamic landscape. A key insight is how phenomena like resting state networks, or RSNs, those patterns of brain activity observed when we're not doing any specific task, are believed to emerge from noise-induced fluctuations around a critical point of instability in the brain's network. It's like the brain is constantly poised on the edge of chaos, ready to explore different activity patterns. This research has culminated in the development of the Virtual Brain, or TVB, an international neuroinformatics platform. TVB allows researchers to simulate whole brain network dynamics by embedding individual connectomes within neural field models. It's a powerful tool for understanding how connectivity drives brain activity, for exploring personalized brain configurations, and even for investigating pathological changes and potential interventions. TVB can even generate realistic simulated brain imaging signals like EEG, electroencephalogram, MEG, magnetoencephalography, and fMRI, functional magnetic resonance imaging, allowing direct comparison with real-world data. Now, let's turn to Chapter 17 by Pinotsis and Friston, which focuses on how we actually use these models to interpret empirical brain data. They delve into the relationship between two main classes of brain models. Neural mass models. These are simpler models that treat a brain region as a point source, describing its activity as a function of time only, usually using ordinary differential equations. Neural field models. These are more complex, considering neural activity as continuous processes across a cortical surface, incorporating both space and time using integral differential or partial differential equations. This allows them to explicitly model spatial parameters like the extent of connections and how fast signals travel across the cortex. To compare these models and test hypotheses against real data, they employ dynamic causal modeling, or DCM. DCM is a sophisticated Bayesian inference technique. In simple terms, it's a way to estimate the parameters of a biophysically plausible model from observed brain imaging data and, crucially, to compare different models based on their model evidence. This model evidence is a balance between how well a model fits the data, its accuracy, and how complex it is, its parsimony. It's about finding the simplest model that best explains the observed brain activity. The chapter presents a fascinating comparison using real brain data. First, they analyzed local field potential, or LFP, data from the auditory cortex. LFP recordings have very high spatial resolution, meaning they capture fine-grained spatial details of brain activity. In this case, the neural field model provided significantly stronger evidence than the simpler neural mass model. This suggests that for high-resolution data, the brain's spatial dynamics are crucial for accurate modeling. However, when they analyzed MEG data from the visual cortex, which has much lower spatial resolution, they found no significant evidence in favor of the neural field model. This highlights a critical point: the best model depends on the quality and resolution of the data you're trying to explain. If your data doesn't resolve fine spatial details, a simpler neural mass model might be just as good or even better from a Bayesian perspective. So, to answer our central question, the brain's dynamic activity is indeed profoundly shaped by its underlying anatomical structure, its intricate local and global connections, and the time delays inherent in signal transmission. Advanced models like neural fields, integrated with platforms like the virtual brain, allow us to simulate and understand these complex interactions. Furthermore, by using Bayesian inference techniques like DCM, we can rigorously test these models against empirical brain imaging data, learning that the choice of model complexity must be carefully matched to the spatial resolution of our observations. This combined approach is unlocking unprecedented insights into how the brain's wiring gives rise to the mind's dynamic symphony. This exploration into the brain's structure-function relationship is continuously evolving. Join us next time on DeepVisus as we continue to explore the intricate ways vision meets depth in the fascinating world of brain science. Stay tuned.